Welcome to second episode of Chiral Drugs. So today let us start our discussion by considering anti-AIDS drug indinavir sulfate, that is antiviral drug. Now let us consider the structure of this molecule indinavir sulfate. First is the synthesis of this compound. Now if you look at the structure of this compound, then you can be able to see that there are two amide bonds are there. One is this amide bond and another one is this amide bond. Now the synthesis of indinavir starts with the formation of this amide bond. So we have to take a suitable acid chloride and amine so that HCl will go and you will be able to get this amide linkage. So for that purpose, the synthesis of indinavir starts from pH, CH2, CH2, COCl. This is one component. Another component is this one. This benzene ring attached with the cyclopentane ring is called as the indene. It's the indene derivative. But this nitrogen and this oxygen, they are protected. So for amine part, it's a tricyclic molecule which will undergo the reaction with this acid chloride. As expected, this hydrogen and chlorine will go in the form of HCl, and first peptide bond will combine these two components so that the right hand side of the compound indinavir is almost ready. Now this compound was subjected to treat with the base. Now base means it will abstract the acidic hydrogen. Now, if we scrutinize the structure of this compound, acidic hydrogen is present at the alpha carbon, which is adjacent to the C double bond O of this amide linkage. Now if from this alpha carbon, alpha hydrogen goes, then the result will be the formation of resonance stabilized carbanion, because this carbanion is not a simple carbanion, it is resonance stabilized because of the electron withdrawing group C double bond O adjacent to this carbanion. Now this carbanion will undergo the resonance stabilization and it will go to the enolate. Now this enolate or the carbon nucleophile will undergo the reaction with the substituted epoxide. So nucleophilic substitution will happen. Now, if this nucleophilic substitution happens, what will be the product? So the combination will be through the alpha carbon and this CH2. Now what will be the structure of this compound? This tricyclic molecule is attached with this amide linkage. This amide linkage is attached with the alpha carbon, beta carbon and the pH. So next to the C double bond O, this is the alpha carbon, this is the beta carbon and the benzene ring combinedly, it is abbreviated as the BN, means the benzyl group. So this part is coming from the previous step, and this CH2 epoxide ring connected with the CH2, it is coming from the this molecule. So after this step, what compound we are getting, that is labeled as A. Now A will undergo the reaction with B. Now let us see what is B. Now in this dotted box, there is some indication about B. What is the structure of B? Now for this, we have to refer the left hand side of this indinavir sulfate. Now if we investigate the structure of indinavir sulfate, then we can see this 6-membered ring where the 2 nitrogen atoms are there at the 1,4 position. And out of these 2 nitrogens, 1 nitrogen next to this nitrogen, we have substituted amide linkage. Now keeping all this part of indinavir, the starting compound of this is one aromatic heterocyclic molecule where the 2 nitrogen atoms are present at the 1,4 position, and next to 1 nitrogen there is that amide linkage, that is as it is what is there in indinavir, means next to the nitrogen alpha carbon is connected with the C double bond O, next is NH, and this nitrogen is attached with the tertiary butyl group. This part is present in indinavir. So if we remember the structure of indinavir, then it will be easy to remember what is the starting compound for synthesis of B. Now when it will be subjected to the catalytic hydrogenation, then this aromatic ring become alicyclic ring, and that compound can be subjected to resolution because indinavir is one chiral compound, and after resolution that amide linkage where it is oriented below, that compound is considered for the further steps towards indinavir synthesis. Now after getting this compound, you see that there are 2 nitrogens. One nitrogen will be Bock protected. Now this Bock protection is happening away from this tertiary butyl group, it is expected because of steady crowding. Although the 2 nitrogens are NH, but out of these 2 NH, 1 nitrogen will be protected. And which nitrogen will be protected? That is which does not have steady crowding. So this nitrogen will be protected. Now after Bock protection, what compound we will be getting? That is considered as a B. Now go back to A. Now A undergoes the reaction with B. So where the reaction will take place. So now if we investigate the structure of A, then we can see that A contains one epoxide ring. So these epoxide rings are prone to nucleophilic attack. So B will act as nucleophile. So in this, if we see the structure of B, then we can make out that this second NH can be the potential source of nucleophile. So this nitrogen will attack the epoxide ring, and we know that the carbon which is unsubstituted in epoxide ring, that will undergo attack by nucleophile. Okay, after nucleophilic ring opening, that molecule will be subjected to the hydrolysis. Now this hydrolysis is because of the deprotection of that indent derivative, where the nitrogen and oxygen were attached with the carbon having the geminal dimethyl group. Now on hydrolysis, this protection will be removed. Now what we will be getting is this compound. Now in one step, this compound will be converted into indinavir. So if we compare this compound versus the final compound indinavir, then we can understand that the nitrogen which is free, that again will be acting as the nucleophile, and in this case that nucleophilic attack will take place to the substituted pyridine. If we see pyridine go to the third position, there will be having the chloromethyl group. So this chloride will go and the nitrogen will attack, HCl will go. So when we are so we will get the indinavir. Now indinavir, by salt formation in another step, it will be converted into indinavir sulfate. Okay, fine. Now the synthesis of indinavir starts with the elimination of HCl and ends also with the elimination of HCl. So in this way we will be able to synthesize the antiviral drug indinavir sulfate, which is extensively used for treatment of AIDS. The full form of AIDS is acquired immunodeficiency syndrome. Now next is mode of action of indinavir sulfate. Now this is that indinavir sulfate is antiviral drug and it is active against HIV, human immunodeficiency virus, and it is just like coronavirus, it is RNA virus, and when this virus comes inside human body, then it leads to the disease called AIDS. The full form of AIDS is acquired immunodeficiency syndrome. Now indinavir is an example of enzyme inhibitor, means it interacts with the active site of enzyme, and the name of that enzyme is protease. And this protease, which protease? Now this protease is present in that retrovirus. That protease can be targeted by indinavir. So this enzyme, what is the role of this protease enzyme? It catalyzes formation of protein and enzyme for the formation of new virus. Now let us see the pictorial representation of mode of action of indinavir. Now let us consider that this is the host cell, means take it for granted this is the human cell. Now this human cell is infected by human immunodeficiency virus. HIV is coming inside the cell. And this is what it is called the, and as because it is the retrovirus, means the RNA virus, this is the viral RNA, single strand viral RNA. Now from the RNA, DNA will be synthesized, and this DNA will come into the nucleus of host, means human cell. Now as soon as this DNA of virus will come inside the nucleus of human cell, it will try to integrate, means it will try to be associated with human cell. So that dark color bold line indicates the integration of RNA virus with nucleus of human cell. Now as it is now associated, it will participate in transcription, and then viral RNA will leave the nucleus and will come to cytoplasm of host cell. Now after transcription, it will participate in translation and viral protein will be formed. Now that enzyme protease cuts the protein from human nucleus or human cytoplasm, and then the new virus, after reconstruction of new virus, it will come out from the human cell. Okay, so this is the mode of action of indinavir, which is an example of enzyme inhibitor. The name of the enzyme is protease. Now what are the interactions? Now we know that types of interactions, non-covalent interactions are hydrogen bonding, ionic interactions, pi-pi stacking, hydrophobic interactions. So let us see what are the, how indinavir is interacting with the active site of protease. So it is basically protease inhibitor. Now if we look at the active site of protease, then we can see that there are 4 pockets are there, which are labeled as S1, S2, S1 prime and S2 prime. There are 4 pockets, S1, S2, S1 prime and S2 prime. Now this molecule has one OH at the middle of the compound. So that OH undergoes the hydrogen bonding, and there are 2 C double bond O's are also there. They also participate in the hydrogen bonding. So let us see what happens here. Now these 2 C double bond O of indinavir and the NH of enzyme protease, there are 4 components are there. 2 are C double bond O. These 2 carbonyl groups are coming from indinavir, and 2 NHs, they are the part of the enzymes. These all participate in hydrogen bonding through one water molecule. So they are hydrogen bond donor and hydrogen bond acceptor. Other than this, there is already I have mentioned at the center of the molecule there is one OH. That OH separately participates in another hydrogen bonding. So these are the varieties of hydrogen bondings, and other than this there are hydrophobic interactions which are present in the four pockets S1, S2, S1 prime and S2 prime. So their S1 pocket has tertiary butyl group, S2 pocket has pyridine nucleus, S1 prime has benzene, and the S2 prime has the indene. So there are important hydrogen bondings and hydrophobic interactions are there in between active site of protease and indinavir. So with this we have finished indinavir sulfate. Now we will go to the next chiral drug, Levo Citrizine. Now this Levo Citrizine is anti-allergic. So with this we are coming to the fourth molecule. The first one is non-steroidal anti-inflammatory drug. Second one is anti-hypertensive. The third molecule is anti-AIDS. Now this fourth molecule is anti-allergic. Now this is Levo Citrizine. So during the synthesis of this Levo Citrizine, this is starting compound, the substrate for the synthesis of multi-step synthesis of Levo Citrizine is the organometallic compound where the benzene ring is connected with the metal chromium. Now it is a eta 6 complex, means there is not a sigma bond is there between chromium and the carbon, but the chromium is connected with the benzene ring through the pi electron cloud. Now this organometallic compound in the 2 to 3 steps it gets converted into this organometallic compound where the two aromatic rings are connected by one carbonyl group. So let us see what are those steps to get this compound from our starting organometallic compound benzene chromium tricarbonyl eta 6 complex. Now this compound is treated with the butyl lithium and another base TMEDA and followed by cuprous bromide in presence of dimethyl sulfide. After that, this compound was allowed to react with the parachlorobenzoyl chloride. So although this molecule has two chlorines, but this chlorine is less reactive because it is attached with the benzene ring, whereas this chlorine is more reactive because it is attached with the C double bond O. Now this chlorine will go because it is more reactive, and in this way the two aromatic compounds are getting connected through the C double bond O. Now this compound C double bond O is subjected to the asymmetric reduction by using the Corey-Boxey Shibata reagent, that is chiral reagent of structure this. In presence of catechol boron. So as a result of this, what happens? Directly we get this molecule where the OH is below the plane and the hydrogen is above the plane, and there is no necessity of going for resolution because we are not getting the racemic mixture. If we get the racemic mixture, then there is a necessity of resolution to proceed further. But as because we are using the chiral reagent to, so we are getting the 1 enantiomer as a major product, and that enantiomer is required to synthesize Levo Citrizine in the following steps. Now when this compound is treated with the fluoroboric acid and in presence of ether, and number 2 is what it is called, the it's the nucleophile again. So what happens is the nucleophilic substitution will happen in this. OH will go and it's SN2, means if you see the product, then here inversion has happened. That hydrogen is above the plane and OH is below the plane, but after nucleophilic substitution, nitrogen is above the plane and the hydrogen is below the plane. So this full molecule, this is a part which is present in Levo Citrizine that we have to remember. Means we have to take the 6-membered ring where the 2 nitrogens are present at the 1,4 position. Now that one nitrogen is free, means it is NH. Another nitrogen will be having a long side chain CH2, CH2, CH2 oxygen, then CH2COH. This one nitrogen is attached with the CH2, CH2O, CH2COOH. Now this OH in this particular final compound has carboxylic acid, but here we can't take carboxylic acid, we have to take the protected ester. Now this compound will undergo the nucleophilic substitution, so OH will be in a Fulton inversion happens, means this is an example of SN2 atom. Now in the next step, that organometallic compound can be converted into the phenyl ring. Means by using this pyridine, eta 6 complex formation can be broken. So that benzene ring, means phenyl ring, will be organochromium compound will be converted into the phenyl ring. So now at the chiral center, phenyl ring is there, parachlorophenyl ring is there, and this heterocyclic alicyclic compound is there with a big side chain, and of course the hydrogen is also there. Now in the last step, by using what it is called the 2 molar HCl, this ester group can be deprotected and it will be converted into the carboxylic acid. So that is what it is called the Levo Citrizine. So in this way we can be able to, this is the synthesis of Levo Citrizine. This is an example of asymmetric synthesis, and as one of the steps we are using the Kuret-Bakshi-Shibata reagent. Now let us discuss the mode of action. This mode of action is, as already at the beginning of the synthesis of Levo Citrizine, I have already mentioned that this is anti-allergic drug, and it targets the H1 receptor. So this is an example of H1 receptor antagonist. Now anti-allergic means when allergic reaction happens in our body, at that time, depending on the situation, doctors may give Levo Citrizine. So when the allergy, now the question is when the allergic reaction happens, when it happens, when allergens interact with B cells. B cells are immune cells which are present in our body. Now mast cells, they are again another type of immune cells. They produce antibodies against allergen or antigen. Now these allergens and antibodies, they interact and histamine is released. So let us repeat this part. So somehow take it for granted allergens have entered in the body, and after entering they interact with the B cells. In addition, mast cells produce antibodies. Now these antibodies and allergens, they fight, and as a result of this interaction there is a release of histamine. Now this histamine interacts with the H1 receptor, histaminergic receptor, which sometimes, not always, leads to itching, sneezing, breathlessness. Means this is called as the allergic condition. Now in order to get the cure from this allergic condition, doctors may give Levo Citrizine. So let us see what is its mode of action pictorially. Now this is H1 receptor which is present in the lungs. Yes. Now histamine, when it interacts with this binding site of this receptor, then finally this interaction leads to bronchoconstriction, and the outcome of this bronchoconstriction is development of allergy. Now in this, R is the receptor in this particular molecule. This is H1 receptor present in lungs. In our body H2 receptors are also there, but the H2 receptors are present in heart. And also in addition with this heart there is one more abbreviation, H. H stands for histamine, that is the neurotransmitter. Now when the doctor gives Levo Citrizine, then Levo Citrizine interacts with the binding site of H1 receptor which is present in lungs. So as because the binding site is already occupied by Levo Citrizine, there is no scope for histamine. So as a result of this, allergic reaction does not occur. Now this is the structure of histamine. So with this we have also finished Levo Citrizine, the fourth chiral drug. Now we will switch over to the fifth chiral drug, verapamil. So let us see what is the structure of this is verapamil and how this chiral drug can be synthesized. So this verapamil synthesis starts from verapamil has chiral center, and eutiomer means more active drug has the S absolute configuration. So during the synthesis of this S verapamil, the substrate, the reaction, the multi-step synthesis starts with the 2S propanediol. Now this compound propanediol, when it is undergoing the reaction with the trityl chloride, so when it undergoes the reaction with trityl chloride, if you look at the structure of propanediol, then you can be able to make out, although this compound contains two OHs, but one is the primary OH which is more reactive and another one is the secondary OH less reactive. So when the first molecule trityl chloride undergoes the reaction with this 2S propanediol, obviously the reaction happens with the primary alcohol, and next is the methyl chloride. That methylation happens in the secondary alcohol. So we get this compound. Now when it undergoes the reaction with the LDA, LDA is non-nucleophilic base. In presence of this carboxylic acid. So what happens? So let us see what is. There is a lactone formation, 5-membered lactone formation. So let us see, this is the lactone formation, C double bond O. So this C double bond O comes from the carboxylic acid, and then this is C double bond O, this is that carbon, next is what it is called the chiral center. That chiral center is this one, this center is this one. So this is attached with the CH2, and this oxygen is this oxygen. So this OMS is actually a leaving group. It is acting as a leaving group. So here the connection is taking place here. Is it okay? Now next is, so this LDA is abstracting actually this acidic hydrogen. The carbon, this carbon is in between carboxylic acid and the aromatic ring. So where is this carbon? This carbon is here. The carbon is attached with the aromatic ring, at the same time it is attached with the C double bond O. Now this compound is treated with the sodium hydride. So again this is the benzylic position, means this position. This position ki hydrogen will go, and then this group is allyl group. It will undergo the reaction with the allyl bromide. So here allyl group will come. That is this compound. It's a 5-membered lactone with two chiral centers on the side by side carbon. One is coming from the starting compound 2s-propanediol and another one we are creating by cyclization and alkylation. Now this compound is subjected to what it is called the ring opening and the introduction of one cyano group at the chiral center, because the cyano group is present in final structure verapamil. So the introduction of cyano group comes here through the ring opening. So this compound, the leftover part is same only. The only modification is this part is common. We have to copy this thing. Then this chiral center is attached with the CH2OH. Ring will open here, and this is gets converted into C triple bond N. The C triple bond N. Now next is this one. This compound ki OH is getting converted with the methyl chloride. OH is getting converted into OMS. And then sodium borohydride and the tertiary butanol, this combination is converting OMS into hydrogen, because means basically that part CH2OMS is getting converted into CH3, means OMS is replaced by one hydrogen, and for that required reagent is sodium borohydride in presence of tertiary butanol. Okay. Now let us see. Now this is what it is called the water addition. This compound is subjected to the water addition, but in a anti-Markovnikov way. So anti-Markovnikov way means that is how it will happen, that already we will be having the ready-made package for the anti-Markovnikov addition of water against the double bond. That is hydroboration followed by alkaline hydrogen peroxide cleavage. So this molecule, when it is treated with the B2H6 followed by H2O2/OH minus, then anti-Markovnikov addition happens and the OH comes to the end of this molecule. Now this compound, when it is treated with the methyl chloride, OH becomes converted into the OMS. Now in this synthesis of verapamil, in the two places we are using this methyl chloride to convert alcoholic OH to the OMS. In both the cases, to make OH a good leaving group, for that purpose only methylation was performed. Now the next is the nucleophilic substitution, and if we and for that purpose we have to remember the structure of the nucleophile. That structure of the nucleophile, that part is directly present in verapamil. So that this nitrogen secondary amine, that nitrogen is the nucleophile and the OMS is the leaving group. So this nitrogen is the secondary amine. It is attached with the CH2CH2, then aromatic ring, where with respect to this linkage, meta position and the para position, two methoxy groups are there. This compound is known as N-methyl homoveratrylamine. Okay, so now with this, the last step is the nucleophilic substitution, and that verapamil synthesis is over. Now verapamil has the absolute configuration. This is the chiral center, and uh, S enantiomer is the eutomer. So let us see the priority, how it happens. Cn is the first priority, aromatic ring is the second priority. The third priority is this one, and the fourth priority is the isobutyl propyl group. Now see what is its mode of action. Now this verapamil means S-verapamil is used for high blood pressure. It is used for angina. Angina means due to some block in the heart, the patient gets the severe chest pain. The supraventricular tachycardia. Tachycardia means the heartbeat is very high, abnormally fast heart rate due to improper electrical activity in the upper part of the heart. So if a patient has like these complications, number 1 is high BP, number 2 is the angina, number 3 is the tachycardia. Then depending on the situation, doctor prescribes his verapamil. Now it is a calcium channel, means calcium channel blocker. Calcium channel comes under the ion channel, and that calcium channel, varieties of calcium channels are present in our body. 4 to 5 types of calcium channels are there, through which calcium 2 plus comes inside the cell, otherwise the outside the cell. These are the calcium ion channels are present in the cell membrane. Now this is S-verapamil is called as the antiarrhythmic drug. So it blocks the voltage gated calcium channel, means calcium channel, which is an example of an ion channel, can be opened, otherwise can be closed. So this opening and the closing can be controlled by the change in the voltage, because the calcium is in, otherwise the calcium is out, so there will be some voltage fluctuation. So these gates are operated because of the fluctuation in voltage. Now if this medicine blocks this calcium channel, what happens? Now blood vessels become wider. It dilates blood vessels, means blood vessels become wider, and so the BP drops. This is the main important points regarding the mode of action of S-verapamil. Now if we see the pictorial representation of the heartbeat and the action potential, means there will be the change in the voltage. So if we see, it is like this. So this diagram is divided into 4 parts. this is minus 80 millivolt. So because of the voltage fluctuation due to the movement of the ions through the heart membranes. So this part, first part is considered as the from the minus 80 it is going to some positive value. So this part is so going to the 0, it is called as a 0 phase. Now from the little up if we move, then that is considered as the phase 1. So phase 0, phase 1. Now next is what it is called the, this is phase 2, then dropping to minus 80, this is the phase 3, and the last part is the horizontal, means parallel to the x-axis, this is phase 4. Now again it will come to the 0 phase 1, phase 1, then phase 2 and phase 3 and phase 4. So there are 5 phases. Phase 0, phase 1, phase 2, phase 3 and phase 4. Now for tachycardia patient, these can be controlled by different types of medicines which can work in the 0 phase or phase 1, phase 2, phase 3, phase 4. So now what is that phase 0 phase? Now 0 phase is known as rapid depolarization. Rapid depolarization means from the negative value, that value is becoming more positive. That is called as the rapid depolarization. Now this step can be rectified by giving sodium channel blocker. Now if doctor wants to control the phase 1, then that can be rectified by giving potassium channel blocker. So that phase 1 is known as the early repolarization. So the 0 phase is associated with depolarization. D for Delhi, depolarization. And the phase 1 is called as early repolarization. Now if we come to the phase 2, and if depending on the situation, if doctor feels that phase 2 can be controlled, so that is called as the plateau phase, and that is controlled by calcium channel blocker. Now depending on the situation, if phase 3 can be arrested, then that is called as the rapid repolarization. And the phase 4 is the resting phase, so that can be controlled by the beta blocker. So this change in the cardiac potential, heartbeat, that has the 5 phases which are called as 0 phase. The name of this is the rapid depolarization. This phase can be corrected by giving sodium channel blocker. Now next is the phase 1, that is called as the early repolarization. This phase can be corrected by giving potassium channel blocker. Now the second phase, which is called as the plateau phase, that can be rectified, corrected by giving the calcium channel blocker. Phase 3, that can be, this is called as the rapid repolarization. And the last part, that is phase 4, is called as the resting phase, that can be controlled by beta blockers. So in these 5 phases, there are 4 different blockers can be given by doctors depending on the judgment of the condition of the patient. It can be the sodium channel blocker, it can be the calcium channel blocker, it can be calcium channel blocker, otherwise it can be the beta blockers. Now we are in the calcium channel blocker. S-verapamil targets the calcium channel. So now let us see that what it is doing. Now this is actually the calcium channel. Now when it is open, then calcium 2 plus is coming inside the cell. Now gate is open. Now this situation is also known as the activated calcium 2 plus channel. Means when the gate is completely open, then calcium 2 plus is entering inside the cell. Now after that, when calcium 2 plus comes inside the cell, then this will be blocked. This gate will be closed, and this is called as the inactivated calcium 2 plus channel. So the first one is the activated calcium 2 plus channel. The next one is inactivated calcium 2 plus channel. Now this inactivated calcium 2 plus channel will be little modification will be there, and that will be some conformational changes will happen. So inactivated calcium 2 plus channel will be converted into the resting calcium 2 plus channel. Now the calcium channel blockers say the S-verapamil delays this actually by blocking. So now this resting calcium 2 plus channel will be converted. It is just before the opening of the calcium channel. So this opening of the calcium channel will be blocked by the calcium channel blockers. Now the example of this class is the S-verapamil, and with respect to this cardiac action potential, it blocks what it is called the Plato phase, means this is the phase 2. Now verapamil is also over. Now we will switch over to the 6th molecule, obviously chiral drug, that is Ethambutol. So Ethambutol is anti-tuberculotic drug, means it is active against tuberculosis. When a person will be having TB, and depending on that patient's condition, doctor may give this Ethambutol. So now let us see, it's a symmetrical molecule. So it is easy to synthesize. Now let us see. Our starting compound is 1-nitropropane. This 1-nitropropane is treated with the base. So in this 1-nitropropane, nitro group is the electron withdrawing group. So therefore the alpha hydrogen will be acidic. Now this acidic hydrogen will be captured by the base, and this carbon nucleophile will attack the delta positive center of the formaldehyde. So this is when it will attack, nucleophile will attack formaldehyde, then what will happen? Hydroxymethylation will happen. Formaldehyde is known for hydroxymethylation. Now this compound is subjected to the, if it is subjected to the catalytic hydrogenation, if we investigate this structure, it has the reducible group is nitro. So nitro gets converted into the NH2, and this molecule has chiral center, but as because we are not using any asymmetric synthesis strategy, so we will get the compound as a racemic mixture. Now when this racemic mixture will be subjected to the resolution, so this compound has the primary amine group, so this is a basic compound. So basic compound, if we want to do the resolution, then we have to take the help of the optically pure acid. As for example, we can take the optically pure tartaric acid or chlorosulfonic acid, camphor sulfonic acid, etc. can be used as optically pure acid. Now for the further step, we have to take the S enantiomer of this compound. Now when this S enantiomer will be subjected to the double nucleophilic substitution, means this will be acting as nucleophile, means this nitrogen will be the nucleophile, and so this molecule has the two living groups. So by controlling the molar proportion of this dichloride and this primary amine, we can be able to replace the two chlorines and can be introduce that NH2 group, means it will obviously this primary amine will be converted into the secondary amine. So the center key 2 CH2 groups are there. This is coming from this 1,2 dichloroethane, and the remaining part, this part from nitrogen, and here also from nitrogen, these are coming from the two molecules of S enantiomer of 2-amino-1-butanol. So with this SS Ethambutol synthesis is over. Now we will discuss the mode of action of SS Ethambutol. As already I have told you that this is one anti-tuberculosis drug. So it is active against the mycobacterial species. Now for bacteria, it what it is called, the inhibits the cell wall. So the target is the cell wall. Now cell wall ki what is the component? It's a cell wall, one of the component is the polysaccharide. So it inhibits which? Now SS Ethambutol inhibits the polysaccharide synthesis during the formation of cell wall of mycobacteria, which is responsible for tuberculosis. Now it inhibits. It is an example of enzyme inhibitor, and in this case the name of the enzyme is arabinosyl transferase. Now this arabinosyl transferase is an enzyme which helps the polymerization of arabinose into arabinon, and then arabinon gets converted into arabinogalactane. So this arabinogalactane is a cell wall component of mycobacteria. So this mycobacteria is responsible for tuberculosis if it comes inside human body. Now let us see the pictorial representation of this enzyme inhibitor, how this SS Ethambutol is inhibiting the active site of arabinosyl transferase. So E stands for arabinosyl transferase, which is an enzyme, and the D stands for the SS Ethambutol. So if it is this ethambutol is interacting with the active site of arabinosyl transferase, then there is no chance of arabinose coming here, and there is no scope for the polymerization of arabinose. So if there is no polymerization of arabinose, then there is no question of synthesis of arabinogalactane. So the cell wall cannot be formed, or if at all it forms for the mycobacteria, the cell wall will be defective. So if the cell wall is defective, then the bacteria will die. So with this we have completed the 6th chiral drug also. Now I will switch over to the seventh one. So that is lomefloxacin, that is uh, antibiotic, means again it is active against the bacteria. Now it is an example of the fluoroquinolone, means this lomefloxacin contains, it's a fluorine, and this is quinolone, quinoline ring की fourth position C double bond O is there. Let us see the synthesis. So for that, as already many times we are discussing, we have to memorize the structure of the final compound, then only it is possible to synthesize without any mistake. Now as already I have told you, this is the fluorine and this is the quinolone. So this is quinoline moiety, but this is at the fourth position with respect to nitrogen. We have the C double bond O, and next to the C double bond O we have the carboxylic acid. Now this part we have to synthesize starting from this aromatic compound. So where we will be having the nitrogens. With respect to this nitrogen, para position ki we have one methyl group, ortho position ki we have one fluorine, and the next to the fluorine, it means in between the methyl group and the fluorine, we have one alicyclic compound. Okay, let us see. So the synthesis starts with the 2,3,4 trifluoronitrobenzene. So we have nitrobenzene. The nitrobenzene ki next position ki 3 continuously fluorines are there, means ortho position, meta position and the para position, 3 fluorines are there, but these fluorines are present because of the various reasons. Only this fluorine will be seen at the final compound, means in lomefloxacin these 2 fluorines will be used for some other purpose. Now when this compound is subjected to the catalytic hydrogenation, nitro group will be converted into NH2. Now it will undergo, this NH2 will undergo the condensation reaction. So that condensation will happen with the EMME. So the full form of EMME is this one. This is diethyl ethoxy methylene malonate. Now the structure of this EMME is this one. So we can clearly understand that when this compound will undergo the reaction with this, the ethanol is going. This alkene is an example of push-pull alkene, means this is pushing electron and this is pushing electron and it is pulling. So this type of alkene where the one carbon is attached with the electron donating group and another carbon is attached with the electron withdrawing group, those are popularly known as push-pull alkene. Now this push-pull alkene, an example what we are taking is the EMME, and EMME will undergo the condensation with this substituted aniline by the removal of ethanol. Now this molecule will be subjected to the intramolecular cyclization. Again one molecule of ethanol will go and we will be getting the preliminary structure of quinolone with the suitably oriented ester group. In the later it will be converted into the carboxylic acid. Now this quinolone moiety will be subjected to the N-ethylation. So this is what it is called. It is treated with the potassium carbonate base, that is ethyl iodide is the ethylating agent in presence of DMF. So nitrogen NH will be converted into the N-ethyl group. Now it will be treated with the boron acetate, and the directly, if we remember this compound, which is also this structural moiety is present in the final molecule lomefloxacin also, that is a 6-membered heterocyclic compound with the 2 nitrogens are present at the 1,4 position, and any one of the nitrogen adjacent we have one methyl group. So now this molecule is the nucleophile, and this nucleophilic substitution is happening. The nucleophilic substitution is happening at this fluorine, central fluorine, because this is para with respect to C double bond O and this meta with respect to this nitrogen. So as because it is nucleophilic substitution, we will be having the reverse order. When C double bond O will be uh, orthopara orienting and the nitrogen will be meta orienting. So with this, this group will be incorporated at the meta position with respect to this nitrogen of quinolone ring. So the last part is that hydrolysis. This hydrolysis is ester will be converted into the COOH. So with this we have finished the synthesis of lomefloxacin. Now we will go to the mode of action, and now it is what it is called the, like previous example, Ethambutol is targeting the cell wall, but this molecule, this is lomefloxacin, targets the DNA synthesis. It is also an example of enzyme inhibitor, but that is also, this enzyme is associated to the DNA synthesis. So it blocks the bacterial topoisomerase 2, which is also known as DNA guidase, as well as the topoisomerase 4. So lomefloxacin targets topoisomerase 2 and the topoisomerase 4. Now see this pictorial representation. This is DNA. And by what it is called the blocking the DNA guidase, what happens now? That supercoiling of this DNA cannot be unfolded. So if it cannot be unfolded, then what will happen? The two things mainly happens. One is the protein synthesis will be under trouble, and the replication is also not possible for the bacteria. These enzymes are associated with bacteria, not associated with our body. So the medicine lomefloxacin targets the topoisomerase, the DNA guidase of bacteria. Now see, this is the active site of DNA guidase and how that lomefloxacin is interacting. Okay, so here you will be having the carboxylic acid. See here, this is the how it is interacting. So this is an DNA guidase is what it is called the an example of metalloenzyme. This has what it is called the magnesium 2 plus in the active site. So there are 3 interactions, major interactions are there. This benzene ring interacts through the pi-pi stacking. This quinolone carbonyl group undergoes the hydrogen bonding. This carboxylic acid undergoes the iron dipole interaction with the magnesium. So with this we have finished the 7th molecule also, that is lomefloxacin. So lomefloxacin has one more thing in this connection I want to tell, that lomefloxacin has chirality in this center. But this we are not synthesizing, just we are taking directly. Okay, fine. So now we will go to the eighth molecule, that is fluorostatin. Now you know that any statin, like it indicates that these type of molecules help to lower the cholesterol inside our body. So fluorostatin is an example of cholesterol lowering agent. So when a person will be having the high cholesterol and what it is called their heart will be under risk, then depending on the situation doctor will give the fluorostatin, so which will be having, this is, you know, this is indole ring is present, and lot of this is nitrogen containing this ring is fully substituted. Nitrogen has isopropyl group, next carbon has full big chain, and here also you have the aromatic ring is there, and again fluorostatin, that flu, it indicates that this molecule contains fluorine. Lomefloxacin also an example of the drug molecule containing fluorine. Fluorostatin also an example of drug molecule having fluorine. Now let's see how to synthesize this molecule. So this molecule is, it is starting from the fluorobenzene. This fluorobenzene is subjected to the acylation. And followed by deprotection. So this is, we are getting what it is called the acylation, means the RCO group will be, this is a C double bond O is directly connected with the benzene ring, and that C double bond O ki next carbon, which is alpha carbon, has the OH group. Now this OH group is actually the living group. Now this compound is getting OH plus ki, what we are bringing is the I. Means this is an example of the apple type of iodination, means it is, this combination is used for the wherever it is used like that for halogenation, that is called as the apple reaction, PPH3 iodine and the imidazole. So the OH primary alcohol CH2OH gets converted into CH2I. Now when it undergoes a reaction with the I, is what it is called the a good living group. I is, so when it undergoes the reaction with the aniline, what happens? The I goes and this aniline comes in. So you have the benzene ring. With respect to fluorine, you have the acyl group here, C double bond to CH2. Now in previous step CH2 was attached with the I, but now it is attached with the NHPH. Now this compound is subjected to the reductive amination. So reductive amination means alkyl group will be incorporated through the imine formation. So first this water molecule like that it will go, and then that will be reduced, that double bond, here you will be having the double bond, the double bond will be reduced by sodium cyanoborohydride. So in this way isopropyl group will be incorporated over this nitrogen instead of direct incorporation of isopropyl group. This is the method how isopropyl group can be inserted in the indirect way. So first is the creating double bond, followed by the reduction by using the mild reducing agent sodium cyanoborohydride. So the remaining things are all what it is called the common. So pH, this nitrogen is attached with the isopropyl group which is coming from acetone. Now this nitrogen is attached with the CH2, then it is attached with the C double bond O. C double bond O is attached with the benzene ring, and the para position we have the fluorine. Now this part, in presence of zinc triplet, it gets converted into the indole. So that combination is called as the Wissler indole synthesis. Usually indole will be synthesized by the Fischer indole synthesis, but in this case there is no chance of going towards the Fischer indole synthesis. So the statin was synthesized by what it is called by taking the help of Wissler indole synthesis. So this cyclization where it is happening, see, with respect to this is C double bond O. This is coming actually here at the ortho position. So this is intramolecular acylation. So acylation is happening. There are two benzene rings are there. So this is actually electron deficient. This is it because of this benzene ring is attached with the electron withdrawing group. This benzene ring is attached with the electron donating group. So on this reaction will happen. The reagent is this part. This is the acylating agent. Acylation is happening here. So in this way, this compound, this part is getting converted into indole. That is the core part of fluorostatin, the indole part. Now what it is called that this molecule is subjected to the Wills-Meyer-Hack formylation reaction by using the reagent in this step is the POCl3 and DMF. Now the formylation happened and then this is subjected to the T-Bay olefination. This is an organometallic compound and the CHO gets converted into the, that is overlapping type of reaction. So this carbon and this CH2 will be making the double bond. Now in the next step this is subjected to the olefin metathesis. So olefin metathesis means this olefin and the another molecule will overlap. So in this case again we have to, this is directly coming from the final molecule. If we know the structure of the final molecule fluorostatin, then only it is possible to write. So in presence of Grab's catalyst, this olefin metathesis happens and then the leftover part is only this ester hydrolysis which will give the final molecule fluorostatin. Now fluorostatin, how it is more, now complete synthesis is over. We are not doing any asymmetric synthesis is here. Directly we are bringing that chiral centers which are present in the fluorostatin. Now what is the mode of action of this fluorostatin? Again this is an example of enzyme inhibitor. Okay, so this is HMG-CoA reductase inhibitor, and now let us see how it is lowering the cholesterol. So see first how cholesterol is synthesized in the liver. This is if we enlarge the liver cell, inside the liver cell, how the cholesterol is synthesizing. Our body, how it synthesizes cholesterol, that is from HMG-CoA. By taking the help of that enzyme is the HMG-CoA reductase, you will be having the mevalonic acid. Mevalonic acid in a multi-step sequence gets converted into cholesterol. Some idea you might be having if you have gone through this biogenesis unit of paper-4. Mevalonic acid, how it gets the folding and gets converted into cholesterol. Okay, so now let us see that this is HMG-CoA, the precursor of cholesterol, and it gets converted into the mevalonic acid. Mevalonic acid in a multi-step synthesis, it gets converted into the cholesterol. So when doctors prescribe the Fluorostatin, which is a cholesterol lowering agent, means it stops or reduces the cholesterol synthesis by blocking the HMG-CoA reductase, which is the enzyme for the conversion of HMG-CoA to the mevalonic acid. Now the full form of HMG-CoA is the 3-hydroxy-3-methyl glutaryl coenzyme. Now the statins are the inhibitors of HMG-CoA reductase enzyme, and this enzyme will be blocked by statins via reversible inhibition, means there is no covalent bond formation. So now see how that non-covalent interaction happens between statin and the active site of HMG-CoA reductase. Now here we will, that isopropyl group undergoes the hydrophobic interaction. This fluorine undergoes the polar interaction. This 2 OHs undergoes the hydrogen bonding, and the COO minus undergoes the salt bridge interaction. So in this way it blocks what it is called the active site of HMG-CoA reductase, so that HMG-CoA cannot be able to convert into mevalonic acid, and finally cholesterol synthesis will be stopped. So with this part 2 is also over. So read all these things carefully, practice thoroughly, so that you will be able to score here. This unit is very scoring. Thank you.